Are we live? Let's see. Cool. Just testing that stream works. New to this. Nice. Alright, we'll mute the tab that's me. Pop out chat. What do we want to do? Well, let's see what screen only, co-create full screen. Oh, does that look better if I go here? Oh yeah, I can't see it. Oh no, I can't see anything. Shit. Well. Yeah. Maybe I'll put AirPods in. Man, why is it all dark? Damn. Gotta put that on the list of things. The screen only give me nothing. Co-create full screen, main scene. Yeah, main scene is not too bad. Hmm. How does it look full screen? Hmm.
And so we get a the big integration. Well, that's the new.
Can I get this to work? Maybe. Maybe not. Oh. Cool. Let's just check some things. Hmm. Yeah, display capture might be the way. Hmm. Well, let's fix that up. Oh, I don't want to have to fix this every time. Very strange how it's capturing the window. I think I just have to remove it. Hmm. 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 Hmm.
develop in this course. And you're probably asking, what do we need a new method of integration for? Well, even in this program, you're going to see cases where Riemann integration is just not good enough. And as the course develops, we'll see more and more examples to show us just what a valuable extension of Riemann integration the Lebesgue integral is. Well, what we want to do in this program is simply to indicate the method that we're going to adopt to extend the Riemann integral. Now, in order to do this, we'll have a look, first of all, at how we've extended our ideas of integration in the past.
Our old ideas of integration have been based on the idea of area. For example, with a very simple function of this kind, which we call the characteristic function of a bounded interval, the integral is in fact the area. It's the base times the height. Then, if we move on to step functions, as they're called, functions like this, which are linear combinations of these characteristic functions, the integral of such a step function is a linear combination of the integrals of the characteristic functions which go into its makeup. That's all very well, but what do we do with a function like this? In M100, we saw that we could approximate its area by taking sums of rectangular areas. The limit of this process was the integral of the function. That approach was developed by Cauchy around 1820. It was fine as far as it went, because at that time, people only thought of things like this as functions. But eventually, one's idea of a function had to change. We really wanted to start talking about discontinuous functions. And when that happened, one had to change one's idea of integral. We had to turn things on their head, on its head, so to speak. Instead of saying, what is the integral of such and such a function, we asked, does such a function have an integral? Well, you've seen that approach in the M231 course, and it's basically due to Riemann around 1870. So let's have a look again at how that approach works. We start with a partition of the interval of integration, and we take the least upper bound of the function on each subinterval. Then, the upper sum u over this partition is the sum of the rectangular areas. In the same way, we take the greatest lower bounds and get the lower sum L. We then consider u and L for all possible partitions and take the infimum of the u's and the supremum of the L's. We say that the function is Riemann integrable if these numbers are equal and their common value is the value of the integral. And that approach does enable us to integrate a lot of discontinuous functions. And it's in that sense that the Riemann integration was an extension of Cauchy's integration. There were functions which were Riemann integrable but not Cauchy integrable. And in the same sense, Lebesgue integration is an extension of Riemann integration. And in particular, it's an extension which takes account of limits of sequences of functions. But before we go into the details of the extension, Alan is going to look again at the Riemann extension of Cauchy to see precisely what properties he would like an extension to have.
Well, in the case of Riemann and Cauchy, what we have is that the Riemann domain includes the domain of continuous functions, what we've called the Cauchy domain. But for an extension, we require more than this. First of all, we require that the values of the Riemann operator should agree with those in the Cauchy operator on the Cauchy domain. And second,
I feel like today, maybe I should make this the thumbnail. Maybe I'm just brain rotted out. This looks like an Among Us to me. Cauchy, Riemann. What is F? Lebesgue integrable? Oh, functions. I guess just functions in general. Well, it's still Lebesgue integrable. Don't know that everything is integrable. But yeah, I had not thought about the difference between Cauchy and Riemann integrable. That'd be a fun thing to think about. What is something which is Riemann integrable but not Cauchy integrable? Let's see. Maybe it's something in which... to think about that, because piecewise continuous does not work.
secondly, we require that the nice properties which hold in the Cauchy domain should carry over to the Riemann domain. For example, like the class of continuous functions, the class of Riemann integrable functions is a linear space. That is, given any two functions in the Riemann domain, then any linear combination of them is also in the Riemann domain. Moreover, like the Cauchy operator, the Riemann operator is linear.
All right, not to nitpick, but if it's AG plus BH, we're thinking this Euclidean. What's wrong with this? Think about it. They should all be on the same line. Well, I guess it's a plane, so they should all be on the same plane, which it does look like they're in the same plane. Damn, they got me. I was thinking of the, what, lambda g plus 1 minus lambda h. Okay, this is fine.
That is, the integral of a linear combination is the linear combination of the separate integrals. So the Lebesgue domain will contain the Riemann domain. It will be a linear vector space. The Lebesgue integral will be a linear operator. Now, what sort of functions are outside this Riemann domain? What sort of functions are not Riemann integrable? Well, let me give you an example.
This is the example they always use. Oh.
The function f assigns the value 1 to x if x is a rational number q in the closed interval 0, 1. And f is 0 otherwise. That is, when x is irrational or outside the interval 0, 1. Let's try to draw the function. Outside 0, 1, f is 0. Inside 0, 1, it's equal to 1 at the rational points. For example, at the points 0 and 1, it's equal to 1. And also at the point 1/2. And again at 1/3 and 2/3, and so on for all the rationals in the interval. But for the irrationals in the interval, it's 0. Well, f is a very peculiar function indeed. We've only got some of points of f here because it's quite impossible to draw all of them. It would look like a smooth curve up here, the values on the rationals, and a smooth curve down here, the values on the irrationals. And, of course, it's not surprising, or perhaps it is, but we'll now show that f is not Riemann integrable. Here's a partition. Let's look at the contribution to the upper and lower sum from just one of the intervals. Since the interval consists of more than one point, there must be a rational number inside it. Now, that's not too hard to prove. So there's a point at which the function equals 1, which is its greatest value in the interval. And so we get this contribution to the upper sum, a rectangle of height 1. But inside the interval, there must also be an irrational point. Again, not too hard to prove. So the function takes a 0 value, which is its least value in the interval. And so we get a 0 contribution to the lower sum. Now, this is true for every interval in the partition. So the upper sum is going to be this area, equal to 1, and the lower sum is this area, 0. And this will be true for every partition. Therefore, the infimum of the u's and the supremum of the l's are 1 and 0. They're not equal. Therefore, the function f is not Riemann integrable. And so the function f is outside our Riemann domain. Well, you're probably saying, if the sort of functions that we get which aren't Riemann integrable are as ridiculous as this silly one, I mean, why bother with Lebesgue integration at all? Let's forget about it.
That's what I was thinking.
Well, the answer is that functions like f, which turn up to be the limit of sequences of integrable functions, are quite common in applications. And in fact, our construction for f shows us that it is the limit of a sequence of Riemann integrable functions. Phi 1 is the function which is 0 everywhere except at the points 0 and 1. Phi 2 has an additional non-zero value at 1/2. Phi 3 has another 2 non-zero values at 1/3 and 2/3, and so on.
I mean, up to the measure
Really,
0
the sequence
set,
converges to the function
it'll just be the
f.
0 function. if this is what they're going to do, maybe not. Because the punchline of all this measurability stuff, don't care about measurable sets or integrating over those in particular, just measurable functions, is that you could just formally say, define a Cauchy sequence of functions, and then the Lebesgue integrable ones are limits of simple functions. And then you can just say, well, the integral of it will be just the limit of the integrals of the simple functions. And that's good enough. That's good enough to just sort of do everything in practice, or most things in practice. But maybe I'll be convinced otherwise. Maybe, well, I don't know if I'll watch all of this. We'll see.
And each term in the sequence is Riemann integrable. For example, let me just consider phi 1. That's 0 everywhere except at these 2 points. Well, by the Riemann construction, I've got to look at the contribution to the lower sums and the upper sums. Well, the contribution to the lower sums is always 0. That's all right. But what about the contribution from these 2 points to the upper sums? Well, in fact, I can surround each point by a rectangle of as small an area as I please. So the infimum will also be 0. So phi 1 is also Riemann integrable, as is phi 2 and phi 3 and each term. So what we have is a sequence of Riemann integrable functions which has as a limit a function which doesn't have an integral at all. Well, if there were any justice in the world, this function, this limit f, would have an integral and its value would be 0. So what's gone wrong? Why do we have this function f which doesn't have an integral? Well, in order to summarize this, Ian's going to look at what's gone wrong in another diagram.
This is a very clever diagram. I actually really love their little Amogus diagrams that they have. This presentation is very good. But I like that they put f on the border of Riemann integrability because f is a limit of Riemann integrable functions. So it should be on that boundary.
Which might help us to put things right.
Here we've got functions on the left and
They got a
real numbers
commutative
on the right.
diagram.
And what Alan has been doing is been looking at a particular function, which was the limit of a sequence of functions. Each function in this sequence was integrable, Riemann integrable, with value 0. So over here, we have a sequence of zeros. This sequence converges to the limit value 0. What Alan showed was that this function we've got at the top was not Riemann integrable, so that we could not go across the top of the picture, but that he suggested that we ought to be able to, and to do it in such a way that the integral of the limit was this value here. Well, our Lebesgue integration definition will do just that for us, but it won't just do it for this very specific function. It'll do it for any function whatsoever which happens to be the limit of a sequence of functions, provided each function in that sequence has an integral, and provided that the sequence of integral values converges.
Yeah, you
So to
do need
recap,
that
what's
last
going to
bit
happen
too.
is that our Lebesgue definition of integration
You can't just
will
have
enable
things
us
go
to
off
go
to
from
infinity.
this side here across here in such a way that the integral of the limit is the limit of the integrals.
Wow.
So the Lebesgue domain will contain the Riemann domain. In fact, it will strictly contain the Riemann domain because it will contain the limits of sequences just like that one. And furthermore, the Lebesgue
They
integral
put an L.
will have the property that the integral of the limit will equal the limit of the integral. Well, that's perhaps a difficult thing to achieve. Now, how did Lebesgue and other people achieve this? Well, they did it in a very cunning way. What they actually did was define the integral of the limit of this sequence by equaling the limit of that sequence of integrals. They got that property to hold by dogma, by definition. Well, that's a very neat trick. But how are we going to make it work practically? Well, for the thing to work, we need a couple of things. First of all, we need that we can define the integral of these functions phi n. So the best thing to do is to take something simple for them, step functions. So we define the phi n as being a sequence of step functions. And secondly, we want that the sequence of real numbers here does have a limit. Well, We can guarantee that if we have an increasing sequence of reals which is bounded above, because we know that has a limit. How do we get an increasing sequence of reals? We can get that by asking for an increasing sequence of step functions. If phi 2 is greater than or equal to phi 1 at each point, then the integral of phi 2 will be greater than or equal to the integral
They're doing bounded
of phi 1.
monotonic sequences.
So we take an increasing sequence of step functions,
Ooh.
and that gives us an increasing
Call my
sequence
friend
of
soon.
reals, and we get that sequence to be bounded by imposing the conditions separately. So this is what our definition would be. If I have an increasing sequence of step functions, such that that sequence of integrals is bounded, and f is the limit of that sequence of functions, then
Endpoint-wise limit.
I define simply the integral of that limit, the integral of f, as being the limit
wonder-
of that sequence
Do
of
you need
integrals.
uniformity here?
Well, that's a very simple definition, and we get two quick results from it. First of all, trivially, that function, that funny function we had before, does have an integral now, and it's 0, because it's simply the limit of a sequence of zeros. And secondly, we get that interesting and important result that the integral of the limit
Much
is
ado
equal
about the
to the
Lebesgue
limit
integral.
of the integral for a sequence of functions. Well, not quite. For a sequence of step functions, by definition. The fact that this holds in general for any sequence of integrable functions will be proved later on in the course. Well, this is all too nice and easy. So the question arises is, can something go wrong? Well, in our definition, we considered every sequence of step functions with these two simple properties. And I talked about the limit of the sequence of functions, f, as if the sequence always did have a limit function. So, can something go wrong? Do we always get a limit to that sequence of functions?
We don't often get something for nothing, and we don't here. You see, by building in the property that we wanted across the top of the board there, we've lost something down here. And what we've lost is related to our concept of convergence. So far, we've been talking about the limit function of this particular sequence, and what we meant by that was that at each point in the real line, the sequence of function values converged to the value of the function at that point. But what can happen, and it's quite easy to give examples, is that we can have an increasing sequence of step functions with bounded integrals which do not converge at every point in the real line. Well, there's one obvious way in which we might be able to get out of this difficulty, or we might think of getting out of this difficulty.
What did he say there again? My poor algebra brain.
We can have an increasing sequence of step functions with bounded integrals which do not converge at every point in the real line.
Increasing sequence of that don't converge at every point in the bounded line. Does it mean an increasing area? Because if it's increasing at every point and it's bounded at every point, it ought to converge. But maybe he means something like Dirac delta type things. Let's hear them give an example.
Well, there's one obvious way in which we might be able to get out of this difficulty, or we might think of getting out of this difficulty. And that's to only look at those sequences of step functions which do converge everywhere. But that turns out to be far too restrictive and not what we want at all. So instead, what we do is change our concept of convergence a little. Instead of talking about the limit function up here, what we're going to talk about is the set of limit functions. And we get these limit functions in this way.
Because they're
What
different
we're going
measure
to
zero
do
sets.
is to say, look at this sequence of step functions down here. At those points where this sequence of function values does converge, then we know precisely what to take as the function values up here. But at those points where such a sequence does not converge, we agree to take any value we like as the value of a limit function. So obviously in this way we're going to get possibly infinitely many limit functions for such a sequence. But then what we do is to say that for every single one of those limit functions we're going to take the value of the integral to be the number we get here, the limit of the sequence of integral values. Well, as it turns out, that's not a disastrous thing to do, because we can say something rather precise about the set of points at which such a sequence does not converge. It's a very small set, and we can say precisely what we mean by a small set. It's what we call a null set. Now, a null set is going to be a set of points in the real line for which we can cover each of the points by some little finite interval. But we can do this in a very cunning way. We can do it such that the total length of all these little intervals is as small as we please. And so what we're going to find is that if we look at any function, like all these limit functions we've just been considering, we're going to find that the value of the integral of a function does not depend on the function values on a null set.
Well, how do Ian's null sets affect our definition? Well, in practice, this is what happens. You give me a function f, and you ask me, find its Lebesgue integral. Well, what I have to do is, I have to find an increasing sequence of step functions, such that the sequence of integrals is bounded, and such that that function you've given me is the limit of that sequence of step functions. And in the light of what Ian has said, of course, it's got to be the limit almost everywhere, and by almost everywhere we mean at every point except possibly on one of Ian's null sets. That being done, I then define the integral of the function you gave me as simply being the limit of the sequence of integrals. Very straightforward. There's one problem that might arise. Suppose there's a different sequence of step functions with the same properties which also has f as the limit almost everywhere. Will that give me a different value for the integral? Is this definition of the Lebesgue integral consistent? Well, that's a crucial theorem, and we prove it later, but the answer is yes, it is. This is a consistent definition. Well, the set of all functions that I can obtain this way, that is, that I can approximate by an increasing sequence of step functions with this property, is called L-inc. Inc meaning increasing.
Oh, increasing.
Though it's not quite the whole of the Lebesgue domain yet, in fact, we're 3/4 of the way there. This is the third stage in a 4-stage process that we use for defining the domain of the Lebesgue integral operator.
Well, what are all these stages? Well, the point is that we are not going to use the Riemann definition of integration directly to give us our Lebesgue definition. Rather, we're going to go right back to the beginning, so to speak, and build up our Lebesgue definition constructively. So that the first stage we're going to look at is to look at functions like this, the characteristic functions of bounded intervals. And for those, we define the integral to be base times height. At the second stage, we're going to look at step functions. That is, functions which are linear combinations of characteristic functions of bounded intervals. And for each step function, we define the integral to be the same linear combination of the integrals of the characteristic step functions. Then we go on to our third stage, and that's the stage we've been spending a little time here talking about, and the stage at which you're going to see quite a bit in the course units. That's when we go from step functions to L-inc. Now, L-inc consists of all those functions which are the limit almost everywhere, that is, except on a null set, of an increasing sequence of step functions with bounded integrals. And the integral of every function in L-inc will be the limit of the sequence of integral values. But why do we need a fourth stage? Well, the point is that we wanted our Lebesgue domain to be a vector space, much like the Riemann domain. But L-inc is not a vector space. It is not closed with respect to taking all possible linear combinations.
Because of negatives?
So we want the vector space spanned by L-inc. And we get that by considering the set of all those functions which are the difference of two functions in L-inc.
Okay.
And we define the integral of such a function to be the difference of the integrals. And that set of functions we call L1, and that is the domain of the Lebesgue integration operator. Well, that's a very brief and I hope useful trip through the basic stages in the construction of the Lebesgue integral. But of course there's a lot more to the details, and these details you'll be seeing throughout the weeks to come. But what we want to leave you with here is the impression, the fact that there are 4 stages in the construction of this integral. these four stages occur not only in the definition of the integral, but in many of the proofs of the theorems that you'll be seeing. And so, to emphasize once again the importance of these four stages, we want to leave you with this reminder.
They're cooking now. Like somebody needs to rap over the beat. Oh shit. Oh. I do like their harmonic analogy here that's implicit. Major scale. Ah, yes. The difference of yeah. I wonder how they did those animations, especially that last one. Let's look at this a little bit. 'Cause this looks all analog. This is just coming down. Well, maybe this is computer generated. When was this? Alan Solomon. Oh, Creative Commons attribution. Who are these guys? Alan Solomon and Ian Day. I bet they were like 21 years old presenting this. Well, maybe we'll come back to more of this. It's kind of fun. But for now, I have to head out. Ugh. Oh, it's been a stress, depressed, and need of rest day.